When is this fake ass product rule actually satisfied? We know in general that the derivative of a product of functions is not the product of the derivatives. Otherwise you wouldn't need to learn the product rule. It would be nice if this was true, but it ain't. And a quick way to see that this is not the case is to look at an example like 2x. So let's have f of x equals 2x. On one hand, we know that the derivative of this function is just 2. So we can write f prime of x equals 2. On the other hand, if we look at this as a product of 2 and x and apply this fake ass pretended power rule, we're gonna get something that ain't 2. So by the fake power rule, f prime of x is the derivative of 2, which is 0, times the derivative of x, which is 1. So we get 0. So clearly, this is not true in general. But just because this isn't generally true, doesn't mean that there aren't some functions that do satisfy it. So let's look for them. Well, it's pretty clear that constant functions are going to work because the derivative of a constant function is 0. And if you take the product of two constants and you apply this fake ass power rule, you're going to get 0 times 0. So it works there. But are there any other examples? Let's begin our search by simplifying the problem a little bit. Instead of looking for these two separate functions f and g, let's just let g and f be the same function, so that we have this. Now, this is actually a differential equation. Let's let y equal f of x. Now, by the chain rule, this left-hand side is going to be 2y dy dx. Now, we have one solution immediately when dy dx is equal to 0, or when y is a constant function. But otherwise, we have this. This is just a separable differential equation. So we have that 1 over 2y dy equals dx. So if we integrate both sides, we're going to get 1/2 natural log of y equals x plus c. And so if we solve for y, we're going to get that y equals c times e to the 2x. So this tells us that taking both functions f and g to be c e to the 2x, where c is some constant, is going to satisfy this fake ass pretending no good power rule. So we have two forms of solutions, constant functions and f of x equals c e to the 2x. But remember, we made that restriction of asking for f and g to be the same function. So what if they're not? Well, I'm not sure if I've characterized all of the solutions to the fake ass power rule, but I have found some more solutions. So to find them, I asked, what's special about 2? Why does 2 work as the coefficient here, and only 2? Well, it's basically because 2 plus 2 and 2 times 2 are equal to one another. They're both 4. So let's look at other numbers that have that property. Well, if we have that AB equals A plus B, then we can write that B equals A over A minus 1. So let's see if these two functions, f of x equals e to the ax and g of x equals e to the a over a minus 1x is going to satisfy the fake ass product rule. So let's begin by taking the product of f and g, and then we'll take the derivative of that. So the product of f and g is going to be the product of e to the ax and e to the a divided by a minus 1 times x. And that's going to come out to be e to the a squared over a minus 1 times x. Now the derivative of that is equal to a squared over a minus 1 times e to the a squared over a minus 1 times x. Now let's compare that to the product of the two derivatives. Alright, the derivative of f is a e to the ax, and the derivative of g is a over a minus 1 times e to the a over a minus 1x. So the question is, when we product these, are we going to get the same thing as before? Well, the product is going to be a squared over a minus 1 times e to the a plus a over a minus 1 x. And if we take that sum, we are going to get a squared over a minus 1 times e to the a squared over a minus 1 times x. So it does look like these two functions, f of x equals e to the ax and g of x equals e to the a over a minus 1x, are going to satisfy this pretending ass fake product rule. So my question to you is, are these all of the solutions? Are these all of the function pairs that are going to satisfy this fake product rule? I honestly do not know. I'm not sure, and I'm not sure I really have the time right now to delve into this further. So I leave that up to you guys. You can comment below if you find other functions that satisfy the fake product rule. But that's gonna have to do it for this one. Thanks for watching. I'll see you next time.
Sorry, 93, I even got it tatted on me. 2012, lady, y'all not feeling sorry. And you know me, without T there probably would be no me, dog. Holler back at me in 2023. Lying bitches up from the nosebleeds, yeah. God's plan.